let's start with the second thing that we need to know, and that thing is a general diffusion process. So we talked about the Langevin equation, and I told you Langevin equation is a kind of a specific kind of diffusion. This is what Langevin tried to explain, a simple diffusion. But in general, you can think about a more generic kind of diffusion. So what is a general diffusion process? A general diffusion process is given by this equation, right? And this equation, when you look at it, first of all, it's a differential equation, right? Because I am dealing with a differential of those parameters, d of x, d of t, d of b, right? So this is why I have differential equation. And b here is a Brownian motion, which we had last time. So this is a stochastic. This is why we call it a stochastic differential equation. Okay? Now, from physics, those of you who can remember physics, anything that you want to explain how it moves, just forget about the Brownian motion. If you want to explain how a projectile, when you just initiate it with some force, right? How it moves and then how it lands, you can explain it by a motion equation, right? And that motion equation is always a differential equation, right? The differential equation is given by the physical rules, right? So this guy, again, since it's a differential equation, is explaining a motion equation, right? The motion, the location of your particle, your projectile at time t, is xt here, okay? And then dt is the differential of the time, so it says every time where it is. And then you're going to have this dB, which is the Brownian motion, which means that in the way you're going to have some stochastic processes impacting your projectile or your particle. And because of that, you cannot talk explicitly about the location deterministically. We can just talk about it stochastically. Everybody's cool? So this is what we call it a diffusion equation. Why? Because diffusion is eventually the motion when you don't have a deterministic idea about the rule, right? So why we explain a particle going in water like moving like that and expanding inside the water. Why we call it diffusion? Because eventually we don't really exactly know what is happening, right? We think that those molecules are just randomly hitting the particles, and then because of that these are diffusing there, right? So eventually diffusion is a motion under some stochastic processes, right? So this is what we call a diffusion. Because of that, any equation of this form is a diffusion equation, right? So Langevin equation was a kind of specific diffusion equation, right? Which had a very specific simple form. Now, here inside this equation, I have this function f term, which could be depending on time t, and also the location. So at every single time, you need to know also the location of the particle to compute this function, right? This is what we call a drift, right? How it's pushed, right? And then the other guy, this g, is a coefficient getting multiplied by the Brownian motion. And I told you this difference in Brownian motion is simply a random process, right? It's a Gaussian process. And this g is eventually computing the variance. This is what we call the diffusion coefficient. Okay? Now, one thing that you might ask me is that why you are showing this arrow here. This is my made-up notation. I hope that it's not going to confuse you more. I try to just use this notation so that later when we get to reverse diffusion, then I just use the other direction. So here what I mean that I'm moving forward in time. So I start at time 0. Now I want to know what is the location at time 1, time 2, time 3, and so on till time t. Okay? So I want to know those locations, so I'm going to move forward. I'm showing that process by x forward t. Okay? Now, as I told you, Langevin equation was very specific form of that one. So this g here that you see, the diffusion coefficient here, was simply square root of 2. And the other thing was simply the score function, right? And what was the property? It was like when you just go on with these processes, then this is going to go forward in time, and at some point you're going to get the distribution which is exactly given by that px, right? That was the property. Everybody's cool? Question? No question? Great. So if you got no question, now how we can use this SDE, right? So, I mean, of course, you can try, analyze it. This is a very complicated thing. But we can use it in this form, exactly like the thing we did with the Langevin equation. We can think of this dx to be a tiny difference, right? Now, we can try that to approximate the location at every single point by a Markov chain, by a random process. For instance, say I just start from time 0, for instance, and then every single time I just shift with difference delta t, right? Now if, for example, I am at time t, and then I just move time, I just go forward in time with a tiny bit of delta t difference, then the change in my location, delta x, is going to be approximately given by this expression, right? So this is the drift term, which is going to be computed exactly at t. This is the difference of time, so I have approximated dt with this delta t. This is the diffusion coefficient. This guy is the difference in the Brownian motion. So what is this difference in the Brownian motion? Do you remember from last time? What kind of random variable is it? It's a Gaussian random variable. Its mean is 0. Its variance is? I'm not going to say that. You should say it. It's? Delta t. Great. Yeah? Its variance is delta t, right? Now, what I can say if I start at time 0, then I just quantize the time. So I start at 0, then I just go one step forward delta t, again, one step forward delta t, and so on, right? At the particular time I, so I have just started from 0, then the first one was delta t, 2 delta t, 3 delta t, and so on. Now I am time I delta t, right? And now I want to know what is the location at time I plus 1 delta t, right? ti plus 1, the next time, right? So I am just breaking down my time axis in this form. This is the time axis t. So I start at time 0. Then I just go delta t. The next one is 2 delta t. And so on. I keep on going. Now I am at time I delta t. I call the location here to be xi. Okay? Now I want to know what is the location when I get at the point I plus 1 delta t, right? So this is what I want to know. I would say, OK, if I know this guy, then I can use that diffusion equation to compute the difference in location, right, delta x. And then I add that delta x to this xi. This is going to be the next location, right? So I'm going to do that. So I'm going to say that the next location is going to be where I am right now, plus this delta x. And the delta x is given by this equation, right? So I'm going to replace that equation here. So this equation is f. The f term is going to be as before. Now I replace x at time t to be the xi that I have. T is ti, which is eventually I times delta t. Delta t is delta t. Gt is g of the time that I am in. And this is the expression that we have for the Brownian motion, the difference in the Brownian motion, right? And we said that this difference in Brownian motion is a normal variable, 0 mean with variance delta t, right? So I can write it down. We did it last time as well. I can write it down in this form, right? I can say this difference, this guy, has 0 mean variance delta t. So it's equivalent to just writing down a square root of delta t times epsilon I. And this epsilon I, oh, I didn't mention it anywhere. OK. Yeah, OK. This epsilon I eventually is 0 mean unit variance. Sorry, I have just if you're taking note, please write it down. This epsilon I is 0 mean unit variance. But in this section, in this chapter, wherever you see epsilon is 0 mean unit variance Gaussian variable. Okay? So this guy is eventually this term. Now I just want to simplify things, so instead of showing it by GTI, I'm writing it down GI. Again, f of ti, I'm writing it down fi, right? So it means the value of that drift term and coefficient at particular time ti, right? Now, this equation is going to help me explain where is the location of the particle at time I plus 1, ti plus 1, when I know the location at time ti, right? Now, you might tell me that why this equation is useful, or why we need this approximation. Well, if we know this approximation, in numerical physics, we can eventually simulate the whole diffusion process, right? So I can start my particle at the particular point x0, then I start just go inside that equation, and that equation is just depending on previous location and some random variable, right? So I just sample some random variable, add it to my location. I'm going to have the new location, right? New location, and so on until the process is over, right? And if I do it like several times, then I start to get a bit of sensing about how it's going to look like when, in practice, a particle is diffused inside the environment, right? So it can help me to simulate the diffusion process, but here in this course, we don't want to simulate a physical diffusion process. We want to use it to somehow simulate a diffusion from noise to data. This is the final purpose, okay? Now, let's look at this forward process. So the forward process is quite simple now. It's the previous point that I was in, some coefficient computed at that point times delta t plus this term, and this term is the only guy which contains noise, right? You have this epsilon, right? And this epsilon is a random Gaussian process, zero mean unit variance. Now, this makes every single guy inside this trajectory random, right? If I start from x0, x1 is random, right? Because there is a noise, right? If I get that x1 and generate x2, that is again random, right? Because x2 is also processed through a random process, right? And I keep on going forward. So I can write it down in this form. I could say I started with some random point p0, right? Some random point that I have sampled from distribution p0, and then I put it inside this process, right? So this process is going to take this x0 to x1, which is distributed by some p1, right? If I know exactly what is p0, then I can compute p1, right? It might be mathematically a bit hard, but I mean not in this particular equation. But if p0 is complicated, it could be a bit complicated to compute, but theoretically it's possible, right? If I know distribution of x0, then I know distribution of x1, right? Then I know distribution of x1, then I can compute the distribution of x2, and I can keep on going till, say, I do I number of iterations, right? So every single time I have one particle, I have one x, which is for us one data sample, which has a particular distribution, right? And this distribution is just progressing, evolving through time by this forward diffusion process, right? Everybody's clear? Question? Great. So if you got no question, one thing that you can think about is that this pix that I'm writing it down is eventually in the regional, diffusion process, is the distribution of the location of your particle when it is at time t, right? You want to know what is the distribution of xt, and that t equals to ti, right? I times delta t, because we have quantized the time axis, right? When I am exactly here, I want to know what is the distribution. I can say approximately the distribution is pix, right? But this is just, physical intuition, physical illustration of this story. For you, this is simply a Markov chain, right? You start with one random process, and then you go through this Markov chain this Markov chain is going to evolve through time, right? And every time it's going to give you a new distribution, right? That's the whole thing that is happening, right? Okay, so this is what we call it the forward process, forward diffusion. Now, in 1982, Brian Anderson wrote a paper in Elsevier, which I'm not sure if it was so well received at that particular time, but quite some time later we liked what he did. And the idea was that you can eventually reverse the process in time. Now, one point that I should indicate here, this is a mathematically known thing, but the key contribution he did was that he just did it for this particular process. So the story is that if you have a Markov chain, right, and you do know the start distribution, then you can just explain what are the next distributions, right? Now you can say that if you know the final distribution of this chain, now you put it here, and now you can always make one reverse Markov chain, which when you are moving backward, the distribution are going to be exactly the same as what you had done in your forward path. You get it? So this is a mathematically known thing, but he tried to do it for diffusion process. So now I'm going to show you the equation, but I don't want you to just pay too much attention to the details. Just take this idea that you can go backward in time. So what does he say? He says that you can, if you know the forward SDE, which was the one I showed you in the previous slides, if you know that equation, then you can build this equation. And this equation is again one SDE, right? And this SDE is a diffusion process, right? When you have SDE, this means that it's a diffusion process, right? Now, when you have this diffusion process, instead of time t, I am showing it by s, okay? And s is eventually the reverse time, meaning that in forward process, you started from 0, you went on till you got to capital T. No, you start at capital T, and at every single time, backward time s, you are going s back, right? You get my point? So now if you want to know where is you in time exactly when you are moving forward, then you need to get that s subtracted from t, right? So if I want to show it here, so this was my time axis, right? This was the time axis. I started at, let me show it, okay. I started at time 0, right? And I went on, so this was t till I get to t, right? When I move in this direction, I'm showing it by t, right? Now I can move in this direction. So I started my particle first here, right? So as it started at here, it was x0. And it went on till it get here, right? xt. Now you have a reverse time. The reverse time is in this direction. This is s. So it says that if you start here, then you can move, as you are just processing inside the Markov chain, inside this process, diffusion, you are moving backward in time till you get here. Everybody's clear? What does it mean? I don't want you yet to understand what it's or demonstrating. I just want you to get what is the reverse process, right? So if you have the forward process with a particular Dre factor f and the coefficient g, you just need to write down this equation here. And this equation is going to explain you the reverse diffusion. Now, what is the property of this reverse diffusion? The key property is that if you start at time t, okay, and when you are starting at time t, the point that you put inside this process is exactly distributed with what you ended up when you were moving forward, okay? If you put that final point inside this guy starts to move backward, and every single backward move, it's going to just realize the same distribution as you had before. Okay? So let me just show it in some details for you. Say I have this equation, okay? And I had this equation. I'm going to write it down or approximate it, doing exactly the same thing as I did before. So if I do that, then I end up again by a Markov chain, right? So here in this Markov chain, xi backward or reverse is the location in the reverse time. So the point here is that when I am moving forward, this is x0, then I'm going to have x1, and so on till I get to xi. Okay? This is when I move forward. Okay? And now when I want to move backward, I'm going to put here x backward 0. This is what I'm moving backward. Okay? And out of this, I use the equation. I compute x backward 1. Sorry. Okay? And I keep on going backward. This is the direction of s. Now if I go backward, 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 I end up here at the particular time that I started when I wanted to go forward. I have my x backward I. Everybody's clear? So this is the forward process. I started x0. Then I just put it in the original, not this equation, this equation. I put it inside this equation. I get x1, then x2, and so on till I get to xi, right? I stop here. Now I have this xi. Now I get back here. I put this xi to be my x backward 0, right? I start with this guy. And now I move backward. X backward 1, x backward 2, and so on till I get x backward I. Everybody's cool? So that was the forward process. Now I am moving backward. Okay? Now, the key point here is that I can build this backward equation. Backward trajectory. X backward 0 is this guy. X backward 1 is this guy, the next one. And so on, I move backward, right? Now, the point is that if I start here by sampling one sample from this distribution, in simple words, if I take this guy and put it here, the thing that is going to happen, every single of these backward samples are going to be the samples of the same distribution corresponding to their forward counterpart. You get it? So, meaning that x backward 1 is going to be distributed with pi minus 1, right? Because here we had this guy was distributed. Oh, okay. Let me just take this just for a while. This guy is distributed by p0. This guy is distributed by p1. And we keep on going till we get to this guy, which is distributed by pi, right? Now, if I sample from pi again, which means that, I can practically take this guy and copy it here, right? If I do that, then after doing the backward process, this guy has a new distribution. What Anderson has shown is that this distribution is again exactly pi minus 1, which was the distribution that you had when you were moving forward previous time. You get it? Then if you go one step again backward, you're going to get pi minus 2, right? Pi minus 3, and so on till you get here. What is the distribution of this guy? It's p0, exactly. This is going to be p0. Everybody's cool? You see the idea? So don't confuse yourself with those equations. I'm going to explain whatever is necessary in those equations later. Right now, I hope that you understood what I mean when I say I'm diffusing forward and backward, right? So I can explain statistically the backward trajectory using that equation, right? Once again, you sample something at p0, you put it inside the forward diffusion, it's going to diffuse till time I, right? And then at time I, you have distribution pi. Now, if you just diffuse with a backward SDE, backward diffusion, and you use exactly the last sample that you had here, then you're going to generate new samples. But the feature of those new samples is that these guys are distributed exactly the same as the guys in the forward. Everybody's cool? if everybody's cool, I have one question. X forward I minus 1, X backward 1. Okay? I'm going to write down this equation. You tell me if I am right or wrong. X forward 1 equals X backward I minus 1. Is it the case? No. Right. Great. So this is not happening. Don't confuse yourself. Okay? This is not happening. They have same distribution, right? They could, I mean, this is a very strong condition. You cannot do it unless you really know what was the sample of the noise sample, right? But this is not happening. The key point is that this guy and this guy have same distribution, right? And this is not a hard thing to do, right? You just need to reverse this stochastic process, which you can do. I mean, this is the whole contribution of Anderson. Everybody's clear? So you can move forward, you can move backward statistically. Cool. If you got no question, then let's go forward and do this, I mean, just represent everything a bit more compactly. So what I'm going to do, I'm going to show the forward path in this form. Okay, this is the forward path. So this QI is essentially that complicated, not too complicated, but messy Markov chain which goes forward, right? So I'm going to say that when I have X at forward at time I, then I have this Q forward at time I, which takes this X forward at time I and computes the next, or sample from the next time, right? So it's going to give me X forward at time I plus 1, right? So this is explaining the forward diffusion that we had, right? Now, what about backward? I can write down the same way. I can say I have this Q backward, and this Q backward eventually starts from the last process, right? And every time I give that last sample into this process, it's going to sample from the previous time, right? Reverse time process, right? And it's going to go backward till the beginning of time, right? Now that I have these two, we have this equivalency. So it says that if you move with the forward diffusion Q forward, you start from x0 with distribution p0, and you keep on going till you get to distribution pi. Then you can give a sample from this distribution pi, and then you move reversely in time, right? So you just take the sample xi from that last distribution you ended up with, and then you give it to the Q backward, Q reverse, and this Q reverse is going to sample from previous times for you, right? Everybody's cool? Question? So you got the main idea, right? You move forward in time, you can move backward in time, is statistically, right? You are not moving deterministically, that's obvious, right? Okay, great. Now, why